64 quasar especially from 6 discovered by the HSC ShowQ project. So everyone here knows the reionization. So the first change of the universe from neutral to ionized. So to observe the reionization, we look at the high-energy quasars. We use high-energy quasars as a background light to measure the transmission along the line of sight. So this indicates the change of the neutral fraction. So in high-D quasar spectrum, we see a transmission here to the blue of the lemma 5 emission line is very low due to the absorption of neutral hydrogen. So by measuring the change of the transmission towards lower shift, we can study the change of the hydrogen neutral fraction. And this region is called the Gunn-Peterson neutral. And high-energy quasars have longer trough, and it provides us a transmission at higher shift. But not only this Gunn-Peterson trough can provide us the information of the reionization, but also the near region, the region around the lemma patch emission lines. And this is also called the H2 bubble, the ionized bubble. And we're studying this. So in quasar spectrum, intrinsic spectrum of the quasar is like the blue lines. But due to the absorption by neutral hydrogen, we observe the red lines. So we define the distance from quasars to where the transmission first drop below 0.1, the near-long radius. And this is an example of quasar spectrum, the transmission spectrum. So we see outside the near-long region, it is more neutral. And this is a very simple physical picture of the near-long radius. The radius is inverse proportional to the neutral fraction of hydrogen and also the redshift. So we expect to see smaller ionized bubbles at higher redshift or in a more neutral environment. But besides the near-long region, the damping wing effect is also very important because the number density of neutral hydrogen affects the profile of the damping wings. But because the high-energy quasar is mostly to lunas and they have very strong lemma emission lines, so it is actually hard to observe the damping wings. So by using quasars and gamma ray burst and lemma meter, we have seen a steep drop of the neutral fraction from redshift 7 to 5. But we can see the uncertainty here is still large due to the limited number of our sample. So we need to add more sample to constrain the neutral fraction. And so far there's around 200 quasars at redshift higher than 6 are discovered, but not all of them are well studied, and only a few of them are used on constraining the neutral fraction. So in our study, we are going to use the 64 quasars from the ShowQ project to reduce the uncertainty in the neutral fraction measurement. And our quasar is redshift 5.8 to 6.9, and they are fainter than the quasars in the literature. And also, this is probably the largest sample used on constraining the realizations. So to measure the lemma high transmission, traditionally we fix the power law continuum to this region and then extrapolate them to here as the intrinsic spectrum. Then we can measure the transmission by dividing the observed flux by the intrinsic flux at each relation speed. But it is obvious that the power law doesn't fit the near region well. So instead we use the PCA, which is we fix the intrinsic spectrum to the right side of the quasar spectrum by using a combination of the eigenspectra of quasars. And then we can predict the blue side. Then we can see here, we have a beta prediction on the neon region. And the eigenspectra, or the principal component spectra, is derived from a huge number of low origin quasars. Okay, so this is a comparison to some older papers. So we are using around 17,000 SDSS quasars extracted to 2.5 to derive our PCS, and we adopt an auto-fit method to fit their spectrum in order to avoid the absorption here. And then we derive those PCS from the red spectrum.
So the solid red is the true spectrum. Which is the true continuum, the solid or dashed? There are two red lines. Which one is the real one?
The solid one.
I see a dashed line below. There are two red lines. Never mind. Go on.
Yes, actually, this method is by use the speed line fitting to the mean flux of each small section, and we reject the flux which is the flux lower than 1 sigma.
Right. So that's a simple empirical way to derive the dashed line. But you're telling us that the dashed line is not really the continuum.
Yes.
Unfortunately, you say it's too low.
I think it depends. For example, if you look at this region, maybe only this one is in this section, so we may use the solid lines. Okay, so this is our PCN fitting to the short tube quasars. This is some example. So now we have a beta fitting on the transmission. We can measure the transmission profile better. But actually we are still trying to improve the PCN fitting, and we are trying to fit the spectra to the longer wavelengths. In this figures we fit the spectra to the right side, and then predict the blue side. But we are trying to fit to the longer side in order to predict the intrinsic spectrum of the whole region. So then we may be able to measure the damping width. For example, if you look at this one, this looks like the damping width, but we didn't have a good prediction on the intrinsic spectrum here. This is too low.
So I agree with you that just lambda to the minus, sorry, I'm really excited about this. The lambda to the minus 1.5 green line is maybe dangerous extrapolation, so you should do better. So your improved estimate is the blue line, which maybe is better. The blue line seems to have some wiggles in it. Sometimes it goes up, sometimes it goes down at different places. You know, sometimes 1180. But it's a continuum. It seems strange that a continuum would have wiggles in it. They're not emission lines.
Yes.
I don't really understand those wiggles.
Because we're combining just combining the.
Yeah, mathematically, well.
Yes.
It's kind of hard to see because all of the interesting part, it's on the left side. That's Lyman alpha at the top, I couldn't see.
This side.
That's Lyman alpha, and the interesting part is short of Lyman alpha. Is that on the left side of the graph or the right side of the graph?
The left side.
Okay, so there's almost no information to the left side of Lyman alpha.
Yes.
I mean, it's just difficult to
But
say.
because we are fitting to this region, so the weighting may, if we, for example, if the weighting of this is larger, then the weighting of here is also larger. But it may not reveal the real continuum here.
Yeah, I'm sure you got a perfect fit to the red side, but I mean on the blue side, it looks featureless.
Yes.
Anyway, it's just slightly strange that there are wiggles in it, but anyway, go ahead.
Okay, so this is some preliminary results. So this is a transmission, the mean lemma alpha transmission of the 64 Q quasars, the red lines, red diamonds. So that basically consistent with the literatures. The transmission dropped to around 0 as to around 6. Because the transmission is already dropped to 0, so indeed we need to use the neon region to measure the neutral fraction at higher shift. And this is the neon radius. These dashed lines are the fitting to the each sample, and the black line is fitting to all sample. And the green line here is the lower shift sample, and red line here is higher shift. So from here, we do see a small evolution of the radius, but this radius not only affected by the neutral fraction of IGN, but also the individual property of the quasars. So it still needed to be studied. And here we didn't include the bad data. For example, some bad PCA fitting or just bad spectral qualities. So now we are working on first improving PCA and also trying to take some spectra to see in order to see a clear damping wing. So this is my summary slide. Thank you.
Questions or comments? Okay, so you use a PCA analysis to predict blue wavelengths. But is it possible to use machine learning to predict instead of PCA? I don't know, but in general speaking, so many PCA can be replaced by machine learning always. So.
I think yes.
I think so.
Yes.
I don't want to be too fussy, but I mean, it looks to me like the blue side of the spectra, I mean, I can just see what you're saying. It's 0. It's about 0. And so it doesn't really matter what model of anything you use, you already can see the transmission for most of those, it's 0. Because the only way that the continuum can go to 0 is if there is 0 transmission.
Yes, but we don't care about this region.
Okay, that region I see is more crucial. So it's really your conclusion about the near zone where you must do this.
Yeah.
So you have to fit the Lyman alpha line also very accurately.
Also, she's studying absorption. So she needs to know where it was.
You're right. You have to know where the Lyman alpha emission is so that you can see how much is absorbed. Yeah. Okay.
Yes, and we're trying to measure this. So to the rate of the lemma alpha is also needed, the intrinsic spectrum.
So you're trying to decide where it goes down to 0? Is that's the question there?
I'm trying to decide where, trying to decide the transmission profile here.
Well, the size is what you want to know, the size of the near zone. And so that's a difficult thing to measure. That's nice data down there. But you're trying to measure where it hits 0. Is that right?
Yes.
It starts out at, I don't know, something 1, and then it goes down to 0. Yeah, it's tough because it's so noisy. I mean, it just fluctuates around 0 rather wildly in the actual data.
Yes.
But, okay.
But we smooth the spectrum.
But that one looks pretty convincing.
I think Tetsuya has a constant different method, right? So you could try, especially when our Polish things quite here. I mean, well, at least it's a different method, right? So you could try. It's a possibility.
Other questions or comments? Now let's thank Nicole again.